So, as a continuation, we are going to actually consider our bend brakes, which is another type that we had considered. And that is the first type that we are going to work with. So, it's actually, guys, nothing here. A bend brake simply uses friction, right? So, it works with or uses friction bend wrapped around part of the outer surface of a rotating drum. So the tension is applied to the friction, which is to the friction bend, using what? Using a lever. The difference in tension on the two sides of the belt creates a braking force. So remember, I told you guys, go through your belt drives so that you understand more of what we are actually working with. So it's actually the basic view of what we are going to have dealing with these two types of bend brakes. So the two types that we're gonna work with in this part, got the types of bend brakes. So according to this source, I want us to consider here there are two types of bend brakes in use. The simple bend brake. Then here we have got block and bend. So according to this source, I think this is TVET series. Yes, it's fine if you work it like that, but I don't want us to use this. I want us to work here with the differential bend here. Differential bend brakes. The one that we call block and bend brakes, it's a type on its own. As we have got the bend brakes, we have got the block, we have got the bend and block as a type. Here we need the types under bend, we need the types under block, the types under bend and block. So this is what I'm trying to say. So as I'm to consider the two types of bend brakes, this is what I'm going to give you guys. And for us to understand more, I'm going to explain in emphasis the simple and also the differential bend brake so that we'll be together. So let us start with the simple bend brakes. The simple bend brakes in this type of brake, one end of the bend is attached to a separate rigid support or to the fulcrum of the lever, and the other end is attached to the lever at a distance from the fulcrum. Take note. At a distance from where? From the fulcrum. So that is the most important part that we are supposed to be having there. That's the important part. So this is the part that we want us to see here. As we have in this presentation, let us try it, okay, like this. We have got maybe, let's consider clockwise rotation and also an anti-clockwise. So if let's say we've got a clockwise rotation, remember the clock moves this way. This is the direction of the clock, clockwise. Clockwise. So as long we are moving like this, it is what? Clockwise. Then anti-clockwise, we are now opposing the other way. This is now anti-clockwise. We are now considering an anti-clockwise. All right. So as we take, guys, once we consider this part, we need to go back to our moments. Taking our moments about the point O, which is about the fulcrum. So this is where we've got our fulcrum here, the point O. So for a simple bend, this is where our point O is going to be. You're going to notice a slight difference where the fulcrum is no longer at this point. That's on a differential bend. All right. So if we're to consider taking moments about the point O, which is our fulcrum, and this is the lever that we are going to be considering. Okay. That is the part that we are saying here. In this type of brake, one end of bend is attached to a separate rigid support or to the fulcrum. One end is support to the fulcrum. And the other end is attached to the lever at a distance from the fulcrum. The other one at a distance from the fulcrum. So we are seeing this one attached to the lever at a distance from what? From the fulcrum. Okay. Then the side of bend that is attached to the support or fulcrum can therefore not exert moment about the fulcrum of that lever. This one we're going to talk, guys. There's nothing that we're going to have at a point which lies on the fulcrum, because remember, when you consider moments, it's force times distance. So there is no distance from here, from the fulcrum. There is no distance. So that is why they are saying the side of bend that is attached to the support or fulcrum here can therefore not exact a moment about the fulcrum of the lever. All right. So that is it. So these are the ones, T1, T2, according to the rotation. Because as you can see here, we had T1 and T2. Now it is changing. It is T1 to T2. So how do you consider this? You consider according to the direction. We move, T1 follows direction. We start from T1. If it is clockwise like this, we move from T1 to T2. From T1 to, in that rotation of a clockwise. So it's from T1 to what? To T2. So when it is an anti-clockwise like this, anti-clockwise rotation, we also do the same from T1, where we end, where we are going. The side is of what? Of T2. So that is the consideration that we are seeing here. Anti-clockwise, T1 going to T2. If it is clockwise, T1 going to T2. So those are the ones that we are dealing with. One attached to the fulcrum and another one on the lever, but at a certain distance from the fulcrum like this. One attached to the fulcrum and another one at a certain distance from the fulcrum. That is what we consider. So this is it, guys. And we've got our drum here, which definitely from the center of this drum to here, gonna be talking of the radius of the drum. We're gonna see where it is needed. All right. And our force, which is the applied force, just a normal force, which is being applied also on the lever, as we can see, which is at a certain distance to the what? To the fulcrum, distance L. So as we can see, guys, T2 is this distance from the fulcrum. F is this distance from the fulcrum, but T1 is there on the fulcrum. So there's no distance. There's no moment that we're going to calculate. If we are to consider here, T2 is the one that is on the fulcrum here. So there's no distance, but T1, as we can see, there's a distance. This one from what? From the fulcrum. So here we're just going to call it L1 so that we understand each other. L1, this is L2. L2 to say the distance corresponding to T2. L1, the distance corresponding to T1. All right, then this is just L, the distance from this force to the what? To the fulcrum as it is. So that is the major part, guys, I think that you need. And applying your forces, as you can see, taking our moments about the point O, which is our fulcrum, we are going to notice that as we have our moments taking moments about O, which is our fulcrum in that case. All right. We are going to notice, all right, as we have, remember our moments, guys, we consider the sum of the clockwise moments being equal to the sum of the anti-clockwise moments. So clockwise, how does the clock move? We guys, okay, we have got this one that is under a clockwise rotation. We are talking about the way the drum here, the drum is moving. The drum is moving in a clockwise. Not to say this is of the moments, no. The issue of moments is on its own. Here it is the rotation of the drum. So they can just give you a diagram without a rotation. Then on the question, they ask you, calculate this. Maybe they want you to find T2, or they want you to find this force, or they want anyone. Maybe on this one, they want you to find T1, or they want you to find this force, no matter that what you're given there, or even the distance. That is where you apply this condition of your moments. Not to say my diagram is under a clockwise, so there's another way of, no. Here it is just the drum. Here, the drum is the one that is rotating in a clockwise. But as it is rotating in a clockwise, how did it affect our diagram? It affected T1 and T2. Remember T1 and T2, how I explained how they move in that way of clockwise or anti-clockwise from T1 to T2, from T1 to T2. That is the effect. That is the only effect. So how do we take our moments? All right. Remember our moments, guys, as we take our moments about the fulcrum, this is where we have about the point O. So remember you're considering here, this is our lever. Here, this one, it's our lever, remember. So let's start with clockwise. It means we are taking these ones which are going this way to the fulcrum. That is clockwise. All right. Anti-clockwise, they are going this way to the fulcrum. That is anti-clockwise, remember. So which one is going in clockwise? T1, don't even talk about this because it is at the fulcrum, this one. So it's a waste of our time to actually consider that T1. Let's just ignore this one, okay? So let's move on to T2. T2, as we can see, it is facing up. So as it is moving towards the fulcrum, it is just going to go this way. This is it, to the fulcrum. So this is what? Anti-clockwise, as we can see this way. T2, from where it is just going to go like this. That is anti-clockwise. So T2 is under anti-clockwise. What about F? F is pointing down, as you can see. So is this going to go this way? It will be going in this way to reach the fulcrum. This is the direction that it's going to take. And which direction is this? Clockwise. So as you can see, this one is clockwise. So we only have one clockwise. We only have one clockwise and one anti-clockwise. So remember, moment, force times distance. So we're going to take our force times the distance back to the fulcrum, which is the whole of this L. This is the formula that we are seeing here. F times L is equal to the anti-clockwise, T2 going to what? To the fulcrum. So it's going to be T2 times the distance. What is the distance? That is our L2, this one. The distance between T2 and what? And fulcrum. So that's our formula. When it is like this, there's nothing. There's nothing. It's just these two, guys. There's nothing here. It's just these two. Just these two. There's nothing there. So there's nothing. So using this, you use this formula when you are asked to calculate the torque. The tension, sorry. Why am I on the torque? The torque is another part on its own. The tension, sorry. When you're asked to calculate what? The tensions. It's T1 or T2. So if they want you to calculate T2, it's definitely a condition like this of a clockwise rotation of the drum. You know that on this formula, there is T2 you can calculate, or maybe they want you to calculate the force, or maybe even the distance. Maybe they might, and I want you to calculate the distance sometimes. All right. So this is what you have. So guys, nothing has changed if you check on this side for an anti-clockwise rotation of the drum. Remember, I said this is the rotation of the drum. It only affected this arrangement of T1 and T2. Only that. If we understand this, guys, we are not going to have a challenge. The reason why is once we have this, if we are to take our moments about the fulcrum, just like here what we did, we are going to notice that the sum of the clockwise moment is equal to the sum of the anti-clockwise moments. So which one is going in the clockwise? Same as what we saw here, does not change, guys. This is our diagram. This is T1 that we are considering going this way, anti-clockwise. This F going this way, clockwise. Nothing has changed. So it's going to be F times the distance back to the fulcrum, which is what? Which is L, is equal to the anti-clockwise. It's T1 back to the fulcrum. So it's T1 times what? Times L1. Just like here, nothing has changed. So as you can see, when it is of this condition of a simple bend break, a simple one, the calculations for T1, F, whatever that you want, is the same, guys, for any part that you're given. Just know the rotation of the drum so that you know exactly this arrangement here. It affects that arrangement only here on this arrangement. So if you do not pay attention on how the drum is rotating now, that's where you end up using T2 where T1 is, or using T1 where T2 is supposed to. No. Pay attention to the rotation of the drum, this part. Once you know that, you are done. Okay? Once you know this, you're done. So we are going to apply this later on in terms of our calculations. Let's see the differential bend brakes. In this type of brake, both bends are attached to the lever at a distance away from the fulcrum. That is how we know this is a differential bend. Both bends. Here, the bends, one was attached to the fulcrum. Another one, a distance away from the fulcrum. One is attached to the fulcrum. Another one, a distance away from the fulcrum, which is attached to the lever. But here, they are saying both are attached to the lever at a distance away from the fulcrum. This is our fulcrum. So it means T1 will be at a certain distance from the fulcrum. T2 will be at a certain distance from the fulcrum. T1 will be at a certain distance from the fulcrum. T2 will be at a certain distance from the fulcrum, depending with the rotation of the drum. So this is what we are seeing. I'm going to explain that. As shown in this fig 2.22, all right? So both sides of the bend can now exact a moment about the fulcrum on the leaf. Both. It's no longer here where we are saying if it is like this, on our formula, we don't see T1 because T1 was on the fulcrum. So we don't see T1 on this formula. If it is this one, T2 was on the fulcrum, so we don't see T2 on the formula when you apply our moments because there's no distance. So it was supposed to be T2 times 0 or T1 times 0. So we are not doing anything if it is like that. So we are seeing that T2 was not there on this formula. If we consider this one, T1 was not there. But in this case, that can never happen because T1 and T2, they are both at a certain distance away from the foreground. Once you understand this, you are done. That's a differential bend. So according to this source, this is the best way I think that we can explain. The other one, yeah, for the TVET, I don't know, guys. You see the TVET series for Mechanotechnics N6. I think they just okay. Some of these words, guys, maybe they might affect you if you are using the textbook, but there's some of the things that they left that is important. We are used to them giving us exactly what we need. But there they were just like beating around the bush. I don't know what happened. I don't know who was the author. I mean, who was the person managing that Mechanotechnics N6. But anyways, that is why, guys, I have to bring other sources to you so that you get important information according to what is needed when you are going to answer your exams. But with that textbook that you're using, please continue to use it. I'm there to make sure there is clarity in that textbook also. So if there's any section that you don't understand in that textbook, yes, let me know about that. So this is it, a differential band. Now we notice our fulcrum is shifted. So how are we going to have our moments if the fulcrum is shifted like this? Still, same way. We consider the drum in a clockwise. Remember, guys, this is all this one. Do not even mind. It's about what? The drum. The drum, the way it rotates, if it is clockwise, as we can see here, it is a clockwise. It affects how T1 and T2 are positioned from T1 to T2. So that's what we see, T1 going to T2. Anti-clockwise, same consideration from T1 going to what? To T2. So T1 is always on the tail from 2, okay? So that is the condition there. So let's consider our moments. Let's start with this one. For a clockwise rotation of what? Of the drum. What is it that we're going to consider? Remember our moments, guys. The condition taking moments about what? About the fulcrum. Clockwise moments, the sum of the clockwise moments must be equal to anti-clockwise moments. So this is what we're going to have. Which ones are for the clockwise, the way the clock moves? This. So you're going to see that it is F like this. It is clockwise. Going to the fulcrum, it is going to go like this. That's a clockwise. All right? Look at T1 and T2. They're facing up. So T2 is going to move this way, which is anti-clockwise. So this is our T2 going to the fulcrum here. So it is going to go in an anti-clockwise. All right. Then if we consider T1 to T2, this is our T1 to the fulcrum, I mean T1 to the fulcrum like this. So it's going to go like this way. This is the direction, this way. So which direction is this? Clockwise. So it is going in a clockwise. So on the clockwise, we have got two things here. The F, we said clockwise. As you can see, guys, it's going to go like this. So it's clockwise. So that is why we've got these two, F times L. On our formulas here, F times what? L, this one, which is F times this distance back. All right, there they made a mistake on the presentation. All right, I thought I was going to edit this one, but I didn't manage to. Time, guys. So let me just correct this one here. I don't know. You see this textbook, guys, the people that were doing them, they were also rushing. I think it was issue of market. Issue of market, the TVET series wants a market. This one, they want a market. They are rushing. They want to remove syllabuses at the same time. These people, I mean, I don't understand. I don't understand. Like, do they want people to pass or now they are now after market? So guys, don't tell them that I said this, but I don't understand. So it was supposed to be like this. It's F, this one. You take the distance force to the what? To the fulcrum. All right? Here. This is our or the fulcrum here. So it's supposed to be there. All right. So I think like this, we can understand each other. Then the same thing here, supposed to end here. All right. So if it is like this, then our formula becomes correct. Our L is supposed to, our L, this one, the distance of F to the fulcrum here, not to T1. No, 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 no. Not to any tension, but to the fulcrum. As we said, taking moments about taking moments so that we understand each other about the fulcrum. This is it. Taking moments about the fulcrum. So we're going to have this. That'll be F times L. You see where L ends? Please be careful there. All right, let's go to another clockwise. We say there's T1. So T1 is times L1, the distance back to the fulcrum. As you can see, this is the distance here from T1 to, that's L1. So that is T1 times what? L1 that we are seeing here. So these are the clockwise. Then to the anti-clockwise, we say there's what? T2. So it's T2 back to the fulcrum here, which is L2, this one. So that is exactly T2 times L2, that distance. All right, so like this is going to be fine. So you can use this formula to find any one of these. As we can see, both are there. T1 is there, T2 is there. Even the applied force is there. This one. So you can use it to find anything. So this is the formula that you're going to end up with, considering that we are working with this differential bend for a clockwise movement of the drum. Then for an anti-clockwise, this is what we have. Nothing has changed, guys. All right. This is now for an anti-clockwise. So taking our moments about this fulcrum, we're going to see that those ones for the clockwise, they never change. It's still the F that we had. So it's F back to what? To the fulcrum. So this is what we have here, our force, F back to the fulcrum, this one. But instead of us having T1, this is now T2. All right, yes, sorry, this is now T2, which is going this way, back to the fulcrum. It's now T2 and what? L2. So this is what we have. Remember, T1 and T2 are affected by the direction of the drum. That is the only part. Nothing has changed. Which one is going in the anti-clockwise? Definitely it's what? Is T1 going this way. So that's T1 times L1 is distance back to the fulcrum here. Nothing has changed. So know the direction of the drum. Know it very well so that you do not confuse these T1 and T2. All right, so once you know this, you have applied all this information. What you need are the formulas. Those are the ones that I said as an individual. I want you to refer back to your N4 Mechanotechnics, working with your belt drives. But anyways, guys, I try by all means to understand that, guys, some of us or some of you are into works, going to work at the same time. You need to come back and cover up your stuff to advance as you are working. And for you to go back to your N4 stuff, it's going to be a lot of time. So let me try and list the formulas that are important. All right. So the first one is going to be on the tension ratio. Tension ratio, as we do understand those belt drives, guys, where we've got tight side and the slack side, this and that. Remember, when you're dealing with the belt drives. So that is the condition that you're going back again. So the tension ratio, that's T1 over T2 is equal to, we said, e to the exponent of micro theta. All right. Where T1 and T2 are simply these tensions, but we understand that T1 is what? The tight side. So T1, that is the tight side tension. Tight side tension, which is actually the fixed end, where we have got the tight side. It can also be referred as the fixed end, the fixed end tension, the fixed end, the tension that is for the fixed end. Tension, guys, is just like force, remember? So it is measured in what? In newtons. All right. Then T2, we do understand that is our slack side. The one that is slack, that is what do we go, guys? You see, English, the disadvantage of English is that what can we say? Something that you want to explain, like you understand it and you want to explain to someone to make it simpler. You might make it difficult because of the way they understand also. Something that can be simpler to you can be difficult for someone to understand in terms of simpler understanding. But I just hope these words, guys, tight, slack, they have a meaning to you. So this is just like a free hand fixed on the tight. All right. Free where it is slack. So that is the free end. All right. So those are the tensions. Remember, this is E, which is already on our calculator, the exponential on our calculator. So guys, we're just going to put that one. But we've got the coefficient of friction. So that is our coefficient of what? Of friction. As we do understand, the coefficient of friction does not have the units. It is just a constant, this one that you are given. Then theta is the angle of contact or the angle of loop. The angle of what? Contact or the angle of loop from our belt drives. We talked about this, and it must be in what? In radians. So also for the conversions, guys, to the radians, it is up to you. When I use the N4 consideration, I explained a lot of things there, if not a lot, but I explained something. But you can also use this. Pi is equal to 180 degrees. Pi in what? In radians. And these are degrees. So you can use any conversion. So if I simply want to convert to radians, mostly conversions, because theta is found in radians. So maybe they can give you theta in degrees. So you take the theta in degrees over what? Over 180 degrees. Then you multiply to whatever pi, this pi that you give, which is a constant pi, whatever that you have will be in degrees. So this is the angle given, the given angle. So here our answer will be in radians straight. It gives us an exact answer. Yes, there are those shorter or shortcuts that you can use, but they are using rounded off values. So you're not going to get exact values, but for this one, it gives you exact values. I'm not saying whatever way that you can use, guys, is wrong. No. I'm not saying that. So this is how these formulas play a role, because someone might be wondering to say, why are we calculating T1 and T2? Yet you were telling us about T1 and T2 here. This is how it works. One of the questions, they will require you to use this formula at the end where you find either T1 or T2. So you must be able to manipulate this formula to find anyone. So let's say I want to find T1. It therefore follows that I can simply cross multiply. I can just take this T2 here. So it simply means therefore T1 is equal to T2 times e to the exponent of micro theta. As you can see, I have made T1 the subject. That is the condition. I can also make T2 the subject from here. Therefore, T2 is equal to what? I just have to divide by this. So it's T1 over E to the exponent of micro theta, like this. So these are the tensions, T1 and T2. If I have any one of these, If I have T2, I can simply use this formula to find T1. If I have T1, I can use this formula to find T2. But one way or the other, we are supposed to go back to these. So as you can see, especially from these two of a simple band where there is only T2 in a formula or T1 in a formula, you will use it to find T1. After that, you then find T2 using now the tension ratio. So they work hand in hand. So never say there's a substitute there to say, if I know the moments are going to save me to find those tensions. If I know the formulas, they are going to save me. Both are going to save you. So you must understand both as an individual. All right, so this is it on our tension ratio. This is just a recap. I was not supposed to even explain much like this, guys. This is just your recap there. All right, then now we're going to move on to another important formula, which is the calculation of the torque. The torque transmitted. So they will need you to calculate the torque transmitted by the band. All right, which can be a condition where they're saying the torque transmitted by a brake drum. They can also say the torque transmitted by they can just say brake on its own. This is just one of the same thing that you calculate there, which is the torque. So which formula can we use? Remember torque, we had this from when we're dealing with clutches, but we're using the forces. So instead of using the forces, now we use tension. So torque is equal to T1 minus T2 times the radius of the drum. So this is going to give us our torque in what? In Newton meters. So this is it, guys. We talked about this. This is our tension of the tight side. This is our slack side. All right. So R there is the radius of the drum. So that is the radius of what? Of drum, which is measured in meters. So with this, guys, we've got our torque. That is what we can have. But the normal way of just maybe we do not have any difference. The torque that is generated by the lever can be calculated also. So let's differentiate between the torque transmitted by the lever. All right, so as we were considering our lever here, so what will be the torque? So we can simply consider the force on the lever, which is the weight. All right, so you can work with the weight on the lever, the resultant. This tension, guys, is the force. But because remember, there is tight and slack side, so we need the difference, just like the effective tension. So it's effective tension that we'll need. But when we talk about the lever, we just consider the force, the general weight, the total weight that you're going to have, or the total force. So you can just say the torque is what? Weight times radius, which is same as force times what? Times radius. So where our R now, which is the radius, we are saying it is the perpendicular distance of the load from the lever pivot. Because here we talk about the lever. So if we say the radius, we cannot say it is the radius of the drum. So we have to consider this. Let's specify this one. Perpendicular distance. So this must be the perpendicular distance of the load which lies on the lever. All right, of the load from where? From the lever pivot, because it lies on the pivot, this one, from the lever pivot. That's it. So if we take it that way, then I think all of us will be in the right direction. So that is the torque transmitted by the what? By the lever. Then the brake system of moments, I talked about it here. Working with moments, I've already explained the issue of moments here from a differential bend, and also here dealing with a simple bend where our fulcrum is at the end point, where it is attached to one of the given tensions. So I'm not going to put much on that because I have explained it. I will end up confusing you guys on what you have already understood. So in detail, I want us to work with more questions, more examples as we shall move on. What else can I explain? Some of these formulas, we'll see them, guys. Power. Some of these ones, we're going to see them. Calculations of power. Remember power. 2 pi nt over 60. We are given the torque, the moment of inertia, mass times k squared, the radius of gyration, which is measured in kilograms meters squared. Talking of the angular acceleration from the torque over the moment of inertia, rad per square second. As we are dealing with the brakes, I say this one, it's a negative because there's a deceleration. We are braking so that the object slows down or the object comes to rest. All those formulas for angular motion, guys, they are not going to change. Theta, it's omega 1t plus half alpha t squared. Those omega, guys, they're not going to change. They are not even going to change at all. So here I'm not gonna waste time. Just for us to understand. But these are some of the formulas that we might need. What else? What else that we might need? We talked of the power, meaning to say you can make the torque the subject of the formula when everything is there. Then, if we are to consider on these moments where the moments are being applied, we are going to see some scenarios where the angle of contact is being applied, or there's a certain angle that is being applied, which will affect our T1 and T2. So I want us to be very careful in that consideration. As we can see, T1 and T2, they are supposed to be vertically, meaning to say these are vertical components. So as an individual, I want you to go through the video. I did a video on vertical components and horizontal components, resultant, this and that. I think it was under engineering science as an introduction, just to understand these horizontal components, vertical components, because it is going to affect you. You see your engineering science. So that one I'm going to explain in examples, guys. I'm not going to do that one. I'll end up explaining a lot of things and confuse others who already have an idea of this part. So as an individual, please go through that video, checking on components. I think, yeah, just go through components, but it's about engineering science. It is just like an introduction. I explained about everything. How do you calculate those? So that is it, guys. On our bendy brakes, I want us to consider this part of our bend brakes. Then in our next classes, we shall be dealing or working with examples. So like I said, TVET series, I'm not going to focus with that because even the examples, guys, I was like, what is happening with TVET series? But I'm going to find ways to bring those questions to you guys so that you prepare for your exams, which are ahead of time.